Hi there, this is Dr. Rishi from the Learners Academy, and today we are going to talk about a very interesting topic called force. Now, force has been one of the most important topics which has been researched for centuries, be it people like Aristotle, to people like Galileo, to people like Newton. All these renowned people have got their fame because of this one topic in physics, and we call it force. In the last year, we talked about force and we defined the force as mass of the body multiplied by acceleration. This year, we are going to go ahead one more step. So, we are going to talk about what force is and how it affects our real life. Last year, we had discussed about force and the body was moving in a straight line. This year, we are going to see how the forces are applied and how things change when the force is applied and the motion of the body is in a rotational manner, or the body is turning. So the body is going in rounds in some way or the other. So now let's go ahead and see what we have hidden in this chapter. Before we go ahead, let us talk about the basic concepts of force. The first thing that we need to know is what is force. Force is a push or a pull which would change the motion or the state of rest or the state of motion of the body. Now, by definition, this is the definition in words. Mathematically, force is first thing, change in its momentum with respect to time, or that is time rate change of momentum, or second thing, mass multiplied by acceleration of the body. So these are the two different mathematical definitions that we use to calculate force. Force is measured in newtons in honor to Sir Isaac Newton. We have defined the unit of force after Sir Isaac Newton because of all the work that he has done in physics, particularly his laws of motion, which have defined force or which have mathematically put the force in a really nice manner. So let's first write down these things for us. So the first thing is force is equal to change in momentum, that is delta P, upon change in time, that is delta T. This is one mathematical formula that we have for force. The other one is mass multiplied by acceleration. Mass of the body multiplied by acceleration. Now, the unit we have for force is newtons. This is the SI unit, which is equal to kilogram meters per second square. Okay, so it either can be written like this, or we can write it as kilogram meters per second square. This is the SI unit. The CGS unit is dynes, and non-SI unit that we generally use is kilogram force. So the other unit that we have is kilogram force, or we can say kgf. Okay, so we've talked about the basics of force, what we have, what is the basic formula for force, and the basic units that are used. Now let us go ahead and discuss about force that is in this year's first chapter. The name of the chapter is force in ICSE. The first topic that we are going to discuss is moment of force and equilibrium. Before we understand what is moment of force, let us first understand motion as a basic thing. There are two kinds of motion that we have. The first one is translatory motion, where the body is going in a straight line. So if you see here, now if we have a car here, and if I push the car like this, the car is going to move ahead. So this kind of a motion, either forward or backward, is called as translatory motion, or translational motion, or linear motion, meaning that the car is moving in a straight line like this, meaning that the car is moving either forward in a straight line or backwards in a straight line. So this kind of motion is called as translatory motion. Now let us go ahead and let us talk about rotational motion. So if I just consider this wheel of the car and I turn it like this, then the wheel is following a rotational motion where it is going in circles. So for a rotational motion, we need a pivotal point or a pivot. In this case, this bar is the pivot and the wheel is turning around this point. Okay. So even if I apply the force in any direction, it is still going to turn in a circular motion or in a rotational motion. Now, if you consider this wheel as a body and I apply a force on it, then you would see that the body is turning. So this is called as turning effect of the force. Though my force is in a straight line like this, the motion that the body follows is rotational motion. So what are the factors on which this is going to depend? There are two factors. First is the magnitude of force that I am applying. So if I am applying how much of force I am applying, that is the first thing that I have. So if I apply a larger force, you would see that the motion would be larger or the turning effect would be larger. On the other hand, the other thing that it would depend upon is where I am applying this force. Where I am applying this force. So if I apply this force at this point, whether I apply the force at this point at the edge of the wheel or whether I apply it at a part closer to the wheel. The closer I go to the pivot, the more force I would need to apply. So the turning effect on the body about an axis is due to the moment of force or torque applied on the body. Now, how do we measure this torque? So the torque applied on this body, on this wheel particularly, would be equal to the force multiplied by the perpendicular distance of the application of the force from the pivot. So effectively, it would be the force that I am applying multiplied by the distance between this point and the edge of the wheel. So now, if I have a body like we had there, we had a circle like this and the force was applied at the edge. This was the pivot then, and let us consider this distance as OA. Then the moment of torque in this case would be, now torque is, the symbol for torque is tau, which is a Greek letter. So this torque is the distance that I have, the force that I am applying multiplied by the distance between the pivot and the point where the force is applied. Now this was a simple circular object that I have. What happens if I have an object that is not circular or that is not a simple figure? Say let us have an object like this and there is a force that is being applied like this on it. So we would first trace the direction of the force and then this is the center. Say let's see that this is the pivot that we have. Then we would always consider the perpendicular distance between O and let us consider this as point B, where the line connecting, it would be the perpendicular line that is connecting the line of force and the distance between the pivot and the perpendicular distance between the pivot and the line of force. So in this case also the torque would be F multiplied by OB. So if you can see, to get the maximum torque, we need to apply the force at a distance farther away from the center. The more the distance, the more would be the torque. The easiest real life example for this is the gear system in our bikes, particularly the bicycles. if you see, the smaller the gear number, say the first gear is always wider or the diameter is larger as compared to the top gear, so that we can have we require less force to create the same amount of torque, keeping the cycle in motion. Now let us go ahead towards the the unit of torque. So this is the formula for torque. This is pretty important. Please make a note of this. Then we have unit for torque is it would be the unit of force multiplied by, so this is the unit of force multiplied by the unit of distance. So I would have kilogram, so I would write it as Newton meter, or this would be the SI unit for torque, and the CGS unit would be dyne centimeter, and the other unit, the kilogram force unit, would again be kilogram force meters. So we can have it as kilogram force meters or gram force centimeters. So these would be the 4 units that we would generally be using when we talk about torque of a motion. So these are the units that we are going to use when we are going to measure torque or moment of force. So both torque and moment of force are one and the same thing. We need to keep this thing in our mind. When we were talking about this wheel turning, there are 2 ways in which the wheel can turn. Either it can turn in this direction, that it is going like this, or it can turn the other way around, that is, it is going in the anti-clockwise motion. So either it can go in the clockwise motion or the anti-clockwise motion. Now by definition, if the torque applied produces an anti-clockwise motion, then it is considered as positive, and if it produces a clockwise motion, that is, it would be going like this, then it would produce a negative torque. So anti-clockwise movement positive, clockwise movement negative. We need to keep this thing in our mind. Let's go ahead with the next topic that is there. The easiest example when we talk about a moment of force is opening of a door. So if you see, we have this door here which is hinged at this part. Now the handle, if you see, is always kept at the further distance from my pivot. So in this case, the pivot is on this line, and if I want to open or close the door, I would have to push it here. If I change the position here, that is, I am closer to the pivot, I would require a larger force to turn the door or to open the door. If I am taking it even closer at this point, the amount of force that I require is immensely high, and I am having very hard time just to open it. Now if I try to push it on this part, which is quite close to my pivot, I would have to give immense amount of force just to move the door slightly. The other easy example that we have is the top stone of a hand flour grinder. The handle is always placed at the farther distance, and the person who's trying to grind the flour is going to move it in a particular direction. Okay, since the handle is kept farther from the pivot, it is easier for the person to move the grinding stone. The next example that we have in our real life is a steering wheel. So currently we have power steering wheels in most of the cars, so the wheels are smaller. However, if we talk about the era where we had manual steering wheels, the steering wheels for larger vehicles like buses and trucks were actually very large. So this was the general size. So the driver would have to put a lot of force just to turn those that wheel. Now here 2 forces would be applied in this direction or in this direction to move the wheel, and that would turn the bus or the truck. The other example that we have is from bicycles. Yes, most of you do use bicycles, so if you would have observed it, your pedals are farther away from the pivot where the gear rotates. This helps you to produce a larger amount of torque so that the wheel can turn, the first gear or the gear at the pedal could turn, which by the chain, by using the chain mechanism would drive the gear on the rear wheel, which would make the rear wheel turn. The next example that we see is something that we use in our real life many times. That's a spanner to open a screw. So a spanner would always have a long handle. The larger the nut it needs to open, the longer would be the handle. Here are some examples of the spanners that are used in the industry, and you would see that the larger the handle, the larger the nut, the larger is the handle. So from all these examples, we can conclude that if we want to produce a larger torque, we need to apply the force at a farther distance from the pivot. Now let us go ahead and talk about a couple. What's a couple? It's a funny notion that we have, but a couple has two forces that are separated by a finite distance, and not just two forces but two opposite forces that are separated by a certain distance. So if I have a body like this, there is a force applied here in this direction, and there is a force applied here in this direction. Now what is important for this system to form a couple? First thing is F1 needs to be equal to F2. If both the forces are equal, then only we would get a couple, and they need to be separated by a finite distance. So what are the necessities? Forces need to be equal, they need to be in opposite directions, and they need to be apart from each other. We cannot apply them exactly at the same point, else what would happen? If I apply this F1 here, there would be no motion in the body. So I would have to apply it at a finite distance, say r, that is the distance between them. And now what does a couple do? A couple produces a purely rotational motion. So there is no translation here. It is a purely rotational motion. Some easy examples of a couple in a real life are, we have a car wrench shown here. We can also have a simple cycle wrench, which is shown here, where we can apply two different forces which are in opposite directions, and they would actually help us to open the nuts in an easier manner. The other example that we have belongs to our real life. If we have to open a cap, so this cap, if I have to open it, I would always apply a force with both of my fingers, one force in clockwise direction, so this force is going in clockwise direction, this force is going in anti-clockwise direction, producing a torque, and I would be able to open the cap of the bottle. We also use same mechanism in key and lock as shown here. The key needs to be turned, so again there are two fingers turning it, one finger it is turning it in this side, one finger in that side, and it would help us to open the lock. Other example would be opening a tap, a faucet. So if you need two fingers to open the faucet, because we are applying two different forces in opposite direction, producing a purely rotational motion, making the faucet open or close. So that was about a couple. So we need to understand the torque that is associated with a couple. So we would be calling it the moment of a couple. So we had moment of force, where we were talking about the rotational effect or the turning effect of force. Now we are having two forces, so we are calling them a couple, and they would also have a turning force, or they would also have a turning effect, and we would be calling it as moment of couple. So let us consider this pen to be a couple where there is a force applied, one in this direction and one in this direction. So when the force, so effectively it would turn this pen in a direction like this. So this is the motion that we are going to get. Now What happens is we have two forces here, F1 and F2. Let this be the center O, and we have OA and OB. So the forces are applied at point A and at point B. O is the center of A and B. Now let us see what happens when we apply these two forces, F1 and F2. So what would be the moment of force at point A? The moment of force would be, now since these forces need to be equal, I would be eliminating these 1 and 2 here from here and just get rid of this. Now, so what do we have here? So we have a force which is applied downwards at a point A, which is at a distance OA. So here let's call this as tau 1 because of this force. It would be equal to F multiplied by OA, and if we have tau 2, which is because of the force F at point B, so it would be F times OB. So what would be the total moment? The total moment would be sum of these two. So I would have the total moment tau would be equal to tau 1 plus tau 2, giving me F multiplied by OA plus F multiplied by OB. But here the forces are common, so we can take them outside the bracket and we write F multiplied by OA plus OB. But OA plus OB is equal to the distance between the two forces. So I can easily write it as it is F multiplied by R, where R is the distance between the two forces, the distance between the application of two forces. Now, let us see how they are moving. What would be the sense of the motion, whether it would be clockwise or anti-clockwise. Since my F is tracing a anti-clockwise path, and if you'd see this F as well is tracing an anti-clockwise path. Since both of them are tracing an anti-clockwise path, the sense of this motion would be in anti-clockwise direction. So this motion would be anti-clockwise. On the contrary, if I had my force in this direction and this force in this direction, I would end up with a clockwise motion. Now since this is an anti-clockwise motion, we would be considering it as a positive motion. So now, we have come to a conclusion where we have concluded that the moment of the moment of couple is equal to F multiplied by R. So in some books it is written as F multiplied by D, where D is this distance. I am considering this distance as R, so we can call it as F multiplied by R. So moment of couple would be the distance multiplied by the distance between the two forces multiplied by the magnitude of one of the forces. Now we come to the next topic, that is equilibrium of bodies. Now equilibrium is a psychological topic as well as it is there in physics, it is there in chemistry, it is literally everywhere. We always talk about balances. So that is what we have in equilibrium. Now here we are going to balance the forces. If the forces are balanced, then only we would achieve a equilibrium. So let us see what equilibrium is when we consider motion, in specific rotational motion. First, let us consider different kind of equilibria. The first type of equilibrium is static equilibrium. Static equilibrium means that a body remains in state of rest when different forces are applied to it. The easiest example would be me going and pushing a wall. If I push the wall, I am applying a force on the wall. According to Newton's third law of motion, the wall is also pushing me back, and our forces are equal and opposite, and they are cancelling each other out, which is making this wall not move. So I can say that the force that is applied by me and the force that is applied by the body or by the wall are in equilibrium. Now at the same time, if I take a chair and I push it, we would not be in equilibrium because the chair would actually move. The other example of a static equilibria would be a person sitting on a chair. The person is exerting force downwards and the chair is exerting force upwards, making them balance each other, and the person would nicely sit there. However, if the chair is weaker, then it might break and that means the force applied by the person would be more. If you ask three people to sit on a chair, there is a chance that the chair might just break, because the force applied downwards would be more than force applied upwards by the chair, which would definitely break the equilibrium. Now let us go ahead with the next kind of equilibrium that we have, that is dynamic equilibrium. Now in dynamic equilibrium, so in static equilibrium the body was stationary, it was not moving. In dynamic equilibrium, the word itself indicates the body is in motion. The best example for a dynamic equilibrium is a raindrop. So when the raindrops fall from the sky, they accelerate, they speed up, and then they reach a velocity, which is their terminal velocity. Now this downward force with which they are falling down, after a certain time, after they leave the cloud, is equal to the upward force that is caused by the drag of the air. So this downward force because of their mass, and this upward force because of the air drag, are balanced. Since both the forces are balanced, the drop does not, the raindrop does not accelerate after that. The other example, the next example is an aeroplane. Aeroplane engines are trying to push the aeroplane up, and the mass of the aeroplane is pushing it down. So many times when flying in a flight, you might have observed that you feel that you are not actually moving unless you actually see outside the window. This is because the force applied by the engines are pushing the aeroplane upward, and the force applied by the mass of the aeroplane is pushing it downwards, and both these forces are balancing each other out, making the plane to stay in an equilibrium. Now let us see a practical example of an equilibrium. So this is a pen in front of me. I can try to balance it like this. So you see the mass in this direction is equal to the mass in this direction. So there are two forces acting, and they are in equal and opposite equal directions. So they are cancelling each other out, and I can easily hold this pen. Now if you see, the support is not exactly at the center. This is happening because of the cap on this end. There's no cap on this end. So you see this side is slightly heavier, so the equilibrium point has actually shifted towards the cap. If I remove the cap, obviously I would have to change it to the other side. If you see, there is a slight change in where I'm holding it, to holding the pen to keep it in equilibrium. So what do we conclude from this? There are two things. First thing is, addition of all the forces that are acting on the body is equal to 0, and second thing, addition of all the moment of torques acting, moment of force or torques acting on the body is also equal to 0, meaning some of them would be in clockwise direction, some of them would be in anti-clockwise direction, and together they would be equal to 0. Now let us talk about the principle of moments. It sounds really complicated, it sounds really difficult. However, it's a very simple thing that we need to understand. Technically, this is something very simple. So when we talk about a couple, we have two forces acting. Now let us have a rod, and let us have a force F1 acting here and a force F2 acting here, and let us have the center here at O. Now what would be the condition for equilibrium, as we discussed with the pen example prior to this, that let's call this as A, this is B. So effectively, for equilibrium to happen, OA multiplied by F1 should be equal to OB multiplied by F2. Why so? Because OA multiplied by F1 is my torque in this direction, that is in the anti-clockwise direction, and my OB times F2 is my torque in the clockwise direction. So effectively, torque in anti-clockwise direction should be equal to the torque in clockwise direction. So whenever we talk about force, whenever we talk about the principle of moments, there is only one simple thing that we need to keep in our mind. The torque in the anti-clockwise direction should be equal to the torque in the clockwise direction. However, this is again the complicated part, because it is the torque that needs to be equal. The forces and the distances may vary. So I can have a larger force. So if I have a larger force on AB, my OA should be smaller, because I have to balance the other side, and vice versa. So if I increase the value of F2, then my O would shift towards B. So this was about equilibrium and principle of moments. Now the most common place where this principle of moments is used is in a beam balance. So a beam balance has two pans. Once we increase the weight in one pan, the other pan goes up. We have to balance them. These kind of beam balances were used prior to this in like 12 years ago, when we had no digital balances. But after we started getting to the digital and the spring balances, we have shifted to them because they are way more accurate. So friends, that was all about moment of force and equilibrium from the chapter Force from standard 10th ICSE. If you have any queries, please feel free to send them in the comment box or drop in whenever possible for you. If you found this video interesting, please give us a thumbs up, do share it with your friends, and subscribe to our channel. This was Dr. Rishi from the Learners Academy. Thank you.